Whenever you use the internet to do almost anything today, you are most likely using some kind of cryptographic protocol in order to secure your communications. When you log into an online account or perform a banking transaction, you use HTTPS and its underlying TLS protocol. Whenever you send a message over WhatsApp or Signal, you use the Signal secure messaging protocol. However, protocols can get pretty complex, and reasoning about their security properties can leave you lost in a labyrinth of logical representations and eventualities. That is why, more than a decade ago, major strides began to happen in automated formal verification. Software such as Verifpal and Tamarin began to appear, making it possible for researchers to write models in which they formally describe the protocol they want to verify and the security goals that it's supposed to accomplish. The protocols that Verifpal and Tamarin have to handle can get pretty intense. Here's a slightly simplified execution of the Signal protocol in which Alice initiates a session with Bob, sends a message, and then receives a reply from Bob. As you can see, when we deploy cryptographic protocols that aim to achieve ambitious levels of security guarantees, such as forward secrecy and post-compromise security, things can get pretty complicated. And yet, every time you send a message over Signal, WhatsApp, Wire, or many other applications, some variant of this exact same protocol is being used to protect what you're saying and to ensure that it's delivered only to the person you intend to say it to. Reasoning about and verifying cryptographic protocols can be interesting and fun work. Wouldn't it be great if we could use automated software to do this stuff? Unfortunately, existing tools tend to be highly specialized and difficult to use. So, Verifpal was designed exactly to make it easy for everyone to reason about cryptographic protocols and to verify their security guarantees, even if you have little prior experience with how protocols work or how they are supposed to be designed. Verifpal accomplishes this by pairing an easy-to-learn modeling language with an intuitive analysis framework that gives you easy-to-understand analysis results. The purpose of this video is to help you get started with using Verifpal. So, let's see what Verifpal can do. Setting up Verifpal on your computer is easy and should not take more than 5 minutes regardless of your computer or operating system. Simply visit verifpal.com and click on Software and Media. If you use Linux or Mac OS, you can then quickly install Verifpal via the Homebrew Package Manager. This is the recommended installation method since it will make updating Verifpal later on an easier experience. You can also download Verifpal in a zip file for Windows, Linux, Mac OS or FreeBSD, or simply compile Verifpal yourself from source code. The Verifpal user manual contains more information on how to do that and is also available for download from the same webpage. Let's try to model a simple protocol that shows an exchange between Alice and Bob in Verifpal. So I'm going to open Visual Studio Code and I'm going to have a Verifpal model opened on the left and a terminal opened on the right to allow me to quickly run Verifpal and analyze my model as I write it. The first thing you want to do in Verifpal is declare the attacker. So there are two types of attacker that you can declare, a passive attacker or an active attacker. A passive attacker is basically someone that can actually look into the network and see what's going on with the communications but not modify them or replace them in any way. An active attacker can do that. An active attacker can drop messages, modify messages, redirect messages, and so it's a particularly much stronger attacker. Let's start with a passive attacker for now and declare our two principals, Alice and Bob. Then we're going to have Alice generate a private key. So we use the knows syntax to do that. She knows a private value A. And then Alice is going to calculate her Diffie-Hellman public key, G to the A, using the following syntax. Alice is then going to send her public key to Bob. And this is the syntax that you would use for a message. Now Bob is going to do something pretty similar. He also knows his private key B. And he generates the public key, G to the B. Bob is going to then know some private message, M, and he's going to choose to encrypt that message to Alice by using the Diffie-Hellman shared secret that can be obtained from doing G to the A to the B. And then Bob is going to send the ciphertext to Alice. Now Alice is going to receive the ciphertext from Bob. She's going to try to decrypt it using the shared secret as she can calculate it, G to the B to the A. And at this point, we want to specify what we want to analyze for, whether the queries that we want to see whether this model satisfies or not. So first you want to see if M achieves confidentiality, is the message confidential? And also you want to understand whether it is the case that if Alice receives E, the ciphertext from Bob, then only Bob could have sent it to Alice. This is what we would call authentication in this context. Now we're going to start with a passive attacker and see whether these properties are fulfilled. So we type Verifpal verify and we link to the model. And we get this error because we actually forgot to send the Bob's public key to Alice. So we fix that, and then once we save the model, we can run verification again. And this time we will be able to see that the passive attacker cannot actually find any flaws in this model, because a passive attacker cannot perform a man-in-the-middle attack, which would be necessary here in order to violate either confidentiality or authentication. So let's change the attacker to an active attacker, an attacker that can actually modify values as they're being sent between Alice and Bob. We see that the result is very different. First, if the attacker impersonates Bob by man-in-the-middling Bob's public key when it's being sent to Alice, in that case, the attacker can impersonate Bob. And we also see that if the attacker does the opposite and man-in-the-middle's Alice's public key instead of Bob as it's being sent to Bob, then the attacker will be able to obtain the contents of the message. So the attack scenarios that we just considered are pretty simple. This is a naive Diffie-Hellman protocol where Alice and Bob have long-term public keys that never change, and they can easily be intercepted by the attacker because the encryption key is being calculated purely as the shared secret resulting from Alice and Bob's Diffie-Hellman keys. But what if we wanted to model something more advanced, like mutual authentication? So if we surround Alice and Bob's public keys as they're being sent in messages with brackets, this would indicate to Verifpal that these are guarded constants. Guarded constants can be read by the attacker but cannot be modified, and this is useful for modeling situations like mutual authentication, where, say, Alice and Bob have already pre-authenticated their public keys to one another. Many protocols and systems offer this feature. For example, Signal and WhatsApp offer it in the form of QR code verification or public key verification, which is also known as fingerprint verification in PGP. So we can then selectively unguard a public key, for example, unguard Alice's public key or Bob's public key, and that would allow us to obtain analysis results based on whose public key is guarded and whose public key is susceptible to modification by the attacker. Another thing to note is that the encryption primitive being used by Bob here is pure unauthenticated encryption. So there's no way for Alice to actually obtain integrity guarantees on the message being shared. However, in Verifpal, we can also use an authenticated encryption cipher with associated data, an AEAD cipher. And here we add an associated data of nil, and then we can obtain authenticated decryption on Alice's side. So notice that we can also add a question mark at the end of the decryption statement with Alice. And so, as you can see here, we have successfully authenticated the message, and the resulting queries are different. Now, what the question mark signifies is that this is a checked primitive. Checked primitives in Verifpal are primitives that are modeled such that if, for example, decryption were to fail, then this particular execution of the model would stop at that point. We assume that both parties abandon their attempts to run the protocol should a authenticated decryption fail or a signature check fail, for example, or an HMAC assertion fail. Now that we've covered a simple protocol that allows us to explore what the Verifpal language looks like, let's look at something more interesting. This is a model of the signal protocol similar to the figure that you saw at the beginning of this video. Here we're modeling Alice and Bob initiating a signal session. Well, Alice is initiating a signal session with Bob, sending an initial message, receiving a second message from Bob, and then sending a third message as a response. So as you can see, Signal is a much more sophisticated protocol where certain public keys are long-term keys and also are supplemented by ephemeral keys. We can see here that we are also guarding Alice and Bob's long-term keys. However, Bob is also sending ephemeral keys, GBS and GBO, which are unguarded. And this models a scenario in which you are using WhatsApp or Signal or Wire, where you have pre-authenticated yourselves. So Alice and Bob have already looked at each other's QR codes or verified public keys and so on. Starting from that point, we can see whether if in Signal the identity keys, which is what we call the long-term keys since they're only used for authentication and not for encryption, are sufficient, guarding the authentication keys, the long-term keys, is sufficient in order to obtain security guarantees on Signal itself, on the session as described here. You'll notice that we're also using authenticated encryption, but that we are not checking the primitives, and this is also an accurate modeling of Signal as it is used, because Signal will not restart a session or mark a session as failed if a couple of messages fail to decrypt, which can happen somewhat frequently, especially in scenarios where there's an unreliable or spotty network connection. So as you can see, the queries are pretty similar to what we had earlier. Confidentiality on all three messages, authentication on messages as they're being sent between Alice and Bob. Now notice a new concept here. We have phases. And so this phase declaration is something that I'm going to remove for now. And we're going to run this model such that Alice and Bob have this session running normally with an active attacker. However, they're also going to leak their long-term private keys. And so we're going to see what happens in that case. Now, as we can see, already we have a bunch of results that are popping up, and this is because, this is for obvious reasons. The attacker can man in the middle the ephemeral keys, but also the attacker, while they are unable to directly man in the middle the long-term public keys that are being used by Alice and Bob because they're guarded as they're being sent over the network in order to model mutual authentication, they do have access to Alice and Bob's long-term private keys as the session is being conducted. And that's why phases will come in handy in a moment. So if we look at the results, nothing is really surprising here. The attacker had advanced knowledge of the long-term private keys for both Alice and Bob and was able to intercept and man in the middle the ephemeral keys as the session was happening. This simultaneous knowledge of Alice and Bob's long-term keys, coupled with the ability to man in the middle of the session, allows the attacker to obtain, to basically break every single query, for Verifpal to find contradictions to every query that we model in this model. Now, let's see what happens if we add a phase declaration before leaking Alice and Bob's long-term keys. Phases are interesting because they allow us to model what would happen if long-term keys were leaked to the attacker strictly after the execution of the session. So the attacker cannot actually use their knowledge of those keys during their man-in-the-middle attack on the sessions. And in that case, we see that none of the queries are contradicted. All of the properties are shown to be obtained in the analysis by Verifpal. And this is a great way to model forward secrecy scenarios where we assume, for example, we want to see whether messages are secure if the attacker is able to steal Alice and Bob's devices after the session has been conducted. Let's conclude this video with resources that might be useful if you want to learn more about Verifpal. The Verifpal user manual is really cool. There's a whole manga on formal verification inside it, and Verifpal goes on adventures, and you might find that interesting. But I also wanted to take a look at primitives, other primitives that Verifpal supports that were not mentioned during this brief tutorial. So as you can see, here we have classical hashing, MAC, HMAC, assertions to compare values, HKDF, and also an interesting new password hashing primitive, which allows us to model password hashing such as PBKDF2 or Scrypt or Argon2. And when used in conjunction with the knows password qualifier, we can essentially model situations where a value is secure as an encryption key if it is first stretched using a password hashing function, but if a password is used directly for encryption, then the attacker would be able to break that encryption and obtain the plaintext. There's also public key encryption like RSA. There's signing primitives. There's also Shamir secret sharing, which allows us to split a symmetric encryption key into multiple values and combine it from only a restricted subset of these values. So all of these are primitives that you can use to build more interesting protocols. Here we also have the upcoming Eurocrypt 2020 affiliated event. There's going to be a whole workshop on Verifpal. I'll also make sure to mention Proverif, Tamarin, and CryptoVerif. Might be interesting to check out if you manage to see this video before Eurocrypt 2020. Also make sure to subscribe to the Verifpal mailing list to keep up to date on releases or to discuss Verifpal news. And if you like, you can donate to support Verifpal, which is a free and open source software project that is run entirely on contributions. So thank you for your interest, and I hope that this video was useful in getting you started with using Verifpal for modeling your own protocols.